Welcome to our quantum deep dive.
Hello!
Today, we're embarking on a really fascinating exploration into quantum spin systems. And our guide for this deep dive is an essay, Quantum Spin System, Grundlage moderner Quantenanwendungen, written by Jorgo Schneppert.
Yeah, Schneppet's work provides a really insightful overview of these systems.
So what are they at their core?
Well, at their heart, they deal with a fundamental property of particles called spin. It's this sort of intrinsic angular momentum.
Intrinsic, okay.
And it's proving absolutely crucial for, revolutionary new ways of handling information.
Exactly. And Schneppert's essay, the goal seems to be giving us a clear understanding, right? The core theories, the research methods used to study them.
Right, the state-of-the-art stuff.
Their applications in cutting-edge tech, and also the challenges, things that still lie ahead.
Yeah, it covers a lot of ground.
It really does. It takes us from the basics, the foundations, through experiments and theory, then into things like quantum computing, spintronics, material science.
And then wraps up with the hurdles and, what might come next.
Okay, let's unpack this then, starting right at the beginning. The basics of quantum spin.
So, at the most fundamental level, you have quantum mechanics. That's the rule book for the microscopic world, right? Where classical physics just doesn't work anymore.
Things get weird.
Things get very weird. And within this quantum realm, spin is a fundamental property. You mentioned intrinsic. Think of it maybe like each particle having a tiny internal compass needle.
Okay, like a direction pointer.
Sort of, yeah.
Okay.
This spin is an intrinsic angular momentum. Keyword. Intrinsic. It's part of the particle itself, not because it's, physically spinning like a little top.
Right, not literal spinning. And for specific particles, like electrons spin 12 particles, the essay calls them, Schneppert points out there are essentially only two options for this internal compass along a chosen direction, say the z-axis.
That's right. We usually call them spin up and spin down.
Up and down. Simple enough conceptually.
It's a helpful way to visualize it, yeah. The spin up, which we label plus 12, and spin down, negative 12 states, they're really the foundation for a lot of these new quantum technologies.
And mathematically, how do we handle this?
Mathematically, we use special tools. Operators and things called polymatrices, usually written sigma x, sigma y, sigma z.
Well, I saw those in the essay.
Think of these matrices as like fundamental operators. They let us mathematically describe and predict how a quantum spin will behave if we try to measure it along different directions, x, y, or z.
Okay, so it's not just a concept, there's hard math behind it.
Oh, definitely.
Now, what I find really interesting looking back is how this whole idea of spin even came about. It wasn't always part of the picture for electrons, was it?
No, not at all. Schneppert recounts how the concept, electron spin, it was proposed by Samuel Goudsmit and George Uhlenbeck back in 1925.
Goudsmit and Uhlenbeck, right?
And their idea, which was pretty groundbreaking at the time, was that this intrinsic angular momentum could explain some really puzzling patterns scientists were seeing in the light emitted by atoms, their spectral lines.
So it solved a mystery, basically.
It helped explain observations that didn't fit the existing theories.
But it wasn't just a theory, like a good guess. Was there experimental proof?
Oh yeah, and relatively quickly, too. The Stern-Gerlach experiments, you've probably heard of them.
Vaguely, yeah. Otto Stern and Walter Gerlach in the 1920s.
That's them. Their experiments provided the first really direct evidence that this internal compass, the spin, is quantized.
Quantized meaning? Discrete, it can only point certain ways.
Exactly. It can only take on specific discrete values or orientations, not just any direction in between. The experiment famously showed a beam of silver atoms passing through a non-uniform magnetic field.
And it split.
It split cleanly into two distinct beams, each beam corresponding to one of the two possible spin states. It was huge.
Wow. So not just confirming spin, but confirming quantization itself.
Precisely. It showed that quantum properties are discrete, not continuous like we assume in the classical world. That has, profound implications.
And as the century went on, this idea of spin, it didn't just stay with single electrons, did it?
No, definitely not. Schneppert points out how the concept expanded. It started encompassing larger systems, think magnetic molecules, even entire crystals.
So moving from the ultra-small to slightly larger scales.
Right. And this expansion, this was really the birth of exciting new fields like spintronics.
Which uses electron spin in electronics, right?
Exactly. And also molecular magnetism, which focuses specifically on the magnetic behaviors of molecules.
Okay, so we've got the history, the discovery. Let's dive a bit deeper now into the theory, the foundations that Schneppert lays out. So more formally, What is quantum mechanical spin?
Well, Schneeppelt really stresses that it's an intrinsic property. There's just no equivalent in our everyday classical world. It is the particle's inherent angular momentum.
Okay, and for those spin 12 particles again?
They can only exist in those two specific quantized states, up or down. And it's crucial, he notes, to distinguish this from orbital angular momentum.
Orbital angular momentum being?
That comes from a particle physically moving around something, like an electron orbiting a nucleus. Spin is something the particle just has, inherently.
Got it. And the math. You mentioned the Pauli matrices. Schneeppelt talks about relationships between them, commutation relations.
Yes, exactly. The commutation relations, mathematically written as C's, J, 2I, Twerky. They sound complicated, but they're fundamental.
What do they tell us, basically?
Essentially, they tell us you can't know everything about a particle's spin in all directions simultaneously with perfect accuracy. If you measure spin along X precisely, you lose precision about spin along Y or Z.
Ah, so it's like the Heisenberg uncertainty principle, but for spin.
It's a direct manifestation of that principle, yes, applied specifically to spin.
Okay. And how do we picture these spin states mathematically? Not just up or down, but maybe a mix.
Right. They're represented using state vectors, often written like U plus U plus or.
Alpha and beta.
They're complex numbers, basically coefficients, and their squared values, alpha and beta, tell you the probability of finding the spin in the up or down state if you were to actually measure it along that z-axis.
So it can be in a superposition, a mix of both, until measured.
Exactly. And Schneeppelt also mentions the Bloch sphere. It's a really clever geometrical way to visualize all the possible states of a single qubit, like our spin 12 particle. Every point on the surface of the sphere represents a unique spin state.
A useful visualization tool, then.
Yeah.
Okay, so particles have spin. They can be in these states, but they don't exist in isolation, do they? What happens when spins interact with their environment or with each other? Schneeppelt calls this section Wechselwirkungen. Interactions.
Right, interactions. This is where things get really interesting and often quite complex. Schneeppelt details several key types. First, there's the Zeeman effect.
Zeeman effect. Heard of that one?
It describes what happens when a spin is put into an external magnetic field. The energy levels associated with the spin states split apart.
They separate.
Yeah. The amount of splitting depends directly on the strength of the magnetic field. Think of it, crudely, like a compass needle having slightly different energy depending on whether it's aligned with or against the Earth's magnetic field. But, quantum.
So applying a magnetic field is a way to control the energy levels of these spin states.
Precisely. It's a key tool for manipulation. Then there's spin-orbit coupling.
Spin orbit. Coupling spin and movement.
Exactly. It's an interaction between the particle's spin and its orbital motion, how it's moving around. This actually arises from relativistic effects, things described by Einstein's theories.
Wow, okay. Relativity creeping in.
It gets everywhere. And finally, Schneeppelt discusses exchange interactions.
Exchange interactions. That sounds like spins talking to each other.
That's a good way to put it. It's a purely quantum mechanical effect. It comes from the Pauli exclusion principle, basically. Two identical fermions, like electrons can't be in the same quantum state, and also the electrical repulsion between electrons.
And what does this interaction do?
It essentially dictates whether neighboring spins prefer to line up in the same direction.
Ferromagnetic, like a regular magnet.
Exactly, that's ferromagnetic coupling.
Yeah.
Or if they prefer to align in opposite directions.
Antiferromagnetic.
Right. The sign of a term called J in the equation tells you which one happens. These exchange interactions are absolutely critical for understanding magnetism in materials.
Okay, understanding these interactions is vital. But how do scientists actually look at these systems? How do they investigate them? Schneeppelt outlines quite a few methods, experimental and theoretical.
Yeah, there's a whole toolkit. On the experimental side, Schneeppelt highlights electron spin resonance.
ESR.
What's that for? It's specifically used to study unpaired electron spins. It works by hitting the sample with microwaves while it's in a magnetic field. When the microwave energy exactly matches the energy difference between the spin states, the Zeeman splitting we talked about.
Resonance.
Exactly, resonance. The spins absorb the energy, and you detect that absorption. It's like tuning a radio. You find the frequency where the system resonates. It tells you a lot about the electron's environment.
That was very sensitive.
It is. Very powerful. Similarly, there's nuclear magnetic resonance, NMR.
NMR, that sounds familiar. MRI scans.
Exactly. MRI is based on NMR. NMR focuses on the spins of atomic nuclei this time, provided they have a non-zero spin. Like ESR, it measures the energy splitting in magnetic field and detects resonance at a specific frequency, which depends on the field strength and the type of nucleus. Hugely important in chemistry and medicine.
Okay. Schneepat also mentions magnetometry and neutron scattering. What about those?
Magnetometry is about measuring the overall magnetic properties of a material, its bulk magnetization. From that, you try to infer what the individual microscopic spins are up to.
Like looking at the forest to understand the trees.
Kind of, yeah. And they use incredibly sensitive devices for this, like SQUIDES, superconducting quantum interference devices, which can measure tiny magnetic fields.
SQUIDES, cool name. And neutron scattering.
Neutron scattering uses beams of neutrons. Neutrons themselves have spin, and they don't have charge, so they penetrate materials easily and interact with the magnetic moments of the atoms inside. It's like using neutrons as tiny magnetic probes to map out the spin structures and interactions within a solid, a sort of magnetic X-ray.
Fascinating.
Yeah.
Okay, that's the experimental side. What about theory and simulation?
Crucial as well. Schneepat mentions density functional theory, DFT.
DFT, I've heard that term in computational chemistry.
Yeah, it's a real workhorse. It's a computational method for calculating the electronic structure of materials, basically figuring out where the electrons are and what their energies are. And it's very good at predicting magnetic properties based on the electron density.
So predicting magnetism from first principles.
Pretty much, yeah. Then there are Monte Carlo simulations.
Like gambling. Random chance.
Sort of. They use random sampling, stochastic methods to study complex systems, especially spin systems near phase transitions. Like, how does a material become magnetic or lose its magnetism as you change the temperature? The Ising model is a classic example, often studied with Monte Carlo.
Okay. And he mentions some more advanced techniques, too.
Yes, tensor network methods. These are quite modern, very powerful mathematical techniques, specifically designed for tackling systems where many spins are strongly interacting or strongly correlated, as physicists say. They provide ways to approximate the incredibly complex quantum states of these systems efficiently.
Sounds computationally intensive.
It can be, but they allow calculations that were previously impossible. Think matrix product states, or MPS, as one example.
Right. And finally, quantum field theory.
Yeah, quantum field theoretical approaches offer a very fundamental framework. They describe spin systems at the most basic level and are good for understanding collective behaviors, like excitations called magnons.
Magnons. Like spin waves.
Exactly, like waves of spin sending that can travel through a magnetic material. Quantum field theory gives us the language to describe those.
Okay, quite a toolbox, both experimental and theoretical. So, with all this understanding and these methods, what are the actual, real-world applications Schneepat highlights? Where is this heading?
Oh, the applications are potentially game-changing. A really big one is quantum computing.
The holy grail, almost.
Pretty much. Spins in solid-state systems, particularly electron spins, trapped in tiny semiconductor structures called quantum dots. These are seen as really promising candidates for qubits.
Qubits, the basic units of quantum information.
Exactly. The idea is you can use the spin-up and spin-down states as the 0 and 1 of a quantum bit. And because they're quantum, they can also be in superpositions of 0 and 1.
And how do you control them?
Typically using precisely controlled external magnetic fields and carefully timed pulses of microwave radiation. You can nudge the spin state around on that block sphere we mentioned.
But it's not easy, right? Schneepat mentions challenges. Decoherence.
Ah, yes. Decoherence, that's the big enemy of quantum computing. It's basically the loss of that delicate quantum state, the superposition or entanglement, because the spin interacts with its environment.
Like noise messing things up.
Exactly. Vibrations in the material, nearby nuclear spins, just random thermal fluctuations. They all conspire to make the quantum state decohere or collapse back into a classical state. The information leaks out.
So how do you fight that?
That's where quantum error correction comes in. Developing clever codes, like the surface code Schneepat mentions, to protect the quantum information, even if some qubits get corrupted. It's a huge area of research.
Okay, quantum computing is one major area. What else? Spintronics came up earlier.
Yeah, spintronics. The core idea here is to use the electron's spin, in addition to, or even instead of, its electrical charge, to carry and process information in electronic devices.
Using spin for electronics, how does that work in practice?
A key component Schneepat discusses is the magnetic tunnel junction, or MTJ. Imagine two thin magnetic layers separated by a really thin insulating barrier.
Okay.
Electrons can quantum mechanically tunnel through that barrier, but the ease with which they tunnel, which translates to electrical resistance, depends strongly on whether the magnetic directions, the spins in the two layers, are aligned parallel or anti-parallel.
So the resistance changes based on spin alignment.
Exactly. That effect is called tunnel magnetoresistance, or TMR. It can be a very large effect. This is the basis for modern MRAM.
MRAM, magnetic memory.
Magnetic random access memory, yeah. It's already used in some niche applications. Its big advantages are non-volatility. It holds data without power.
Like flash memory.
Right, but potentially much faster and more durable. There's also a lot of research into spintronic logic devices, aiming for computers that are much more energy efficient than current ones.
Very cool. Using a fundamental quantum property for better memory and potentially processors. What about material science and nanotechnology?
Schneppat touches on that too. Things like magnetic nanoparticles and molecular magnets.
Molecular magnets, single molecules acting as magnets.
Yeah, exactly. Some complex molecules, called single molecule magnets, or SMMs, can trap a magnetic moment and exhibit really interesting quantum phenomena, like their magnetization tunneling through an energy barrier. People are exploring these for ultra-high density data storage, maybe even components in quantum computers.
As nanoparticles.
Magnetic nanoparticles have potential in areas like targeted drug delivery guide the particle with magnets, or as contrast agents in medical imaging, like MRI.
Speaking of medical, functionalized spins.
Right. You can attach spin labels to molecules. In chemistry and biology, these act like tiny spies. You can use ESR to track these spins and learn about molecular structures or how molecules move and interact. And as we said, they can enhance contrast in MRI scans.
So applications from computing and memory to medicine and materials, it's incredibly broad.
It really is. The potential is huge.
But as always, there are hurdles. Schneppat points out some significant challenges we still need to overcome.
Absolutely. A major one is always scalability and control. We talked about decoherence.
Keeping the quantum states alive.
Right. And precisely manipulating individual spins, especially when you want to build systems with thousands or millions of them. That gets incredibly difficult. You need very localized fields and exquisite control.
And the environment is always fighting against you.
Pretty much. Thermal energy, just heat, causes random fluctuations. Boltzmann distribution describes the probabilities, which disrupt the delicate spin states, interactions with lattice vibrations, phonons, other nearby spins, nuclear spins. It's a constant battle to isolate and control the quantum system.
And technologically, are our tools good enough?
Well, we're always pushing the boundaries. Schneppat highlights the need for even more sensitive instruments, better magnetometers like those skewides to detect tiny fields, more precise lasers and microwave sources to manipulate the spins.
And materials.
Crucial. Developing new materials with specific, tailored spin properties is key. Things like Heisler alloys or topological materials that have unique spin behaviors. And we need advanced synthesis methods like molecular beam epitaxy, MBE, to create these materials with atomic layer precision.
So better tools, better materials. What about our understanding? Are there theoretical gaps too?
Oh, yes. Definitely. Describing systems where many spins are strongly interacting, that strong correlation problem we mentioned, is still a major theoretical challenge.
Even with things like tensor networks.
They help enormously, especially for one-dimensional systems. But tackling large two- or three-dimensional strongly correlated systems is, well, hard. Methods like the density matrix renormalization group, DMRG, related to tensor networks are powerful but have limitations.
And fundamental questions remain.
Yeah, like the exact connection between the quantum description and the classical world we observe. Schneppat briefly mentions things like the Wigner transform, which is a mathematical tool used to try and bridge that gap, representing quantum states in a way that looks a bit more like classical phase space.
Okay, challenges in control, technology, and theory. Looking ahead then, what are the future perspectives Schneppat outlines? Where do we go from here?
He really emphasizes the need for interdisciplinary approaches, bringing together physicists, chemists, material scientists, engineers. Everyone needs to work together.
Breaking down silos.
Exactly. Nanotechnology will obviously continue to be vital, providing the tools to build and probe these systems, and computational simulations will become even more important as systems get more complex.
And you mentioned AI earlier.
Yes, Schneppat highlights the growing role of artificial intelligence. AI and machine learning are starting to be used for things like accelerating the discovery of new materials with desired magnetic properties.
Searching through possibilities faster than humans can.
Right. Or speeding up those complex simulations we talked about, and even potentially finding better ways to design and optimize those crucial quantum error correction codes for quantum computers.
AI is a tool for scientific discovery itself.
Increasingly so, yes.
So finally, the big picture vision. What applications might we actually see down the road?
Well, the vision Schneeppert paints is one where quantum technologies based on spin systems become practical, maybe even commercial. Fault-tolerant quantum computers capable of solving currently impossible problems in drug discovery, materials science, optimization.
That would be revolutionary.
Absolutely. Also, continued advances in spintronics leading to ultra-fast, incredibly energy-efficient computing and data storage, and highly sensitive quantum sensors based on spins for navigation, medical diagnostics, fundamental science.
And these could impact global challenges.
Potentially, yes. Think about energy efficiency spintronics could drastically reduce the power consumption of computing. Or data security quantum communication methods, some potentially linked to spin systems, offer fundamentally secure communication based on quantum laws.
So wrapping up our quantum deep dive, guided by Yorgo Schneeppert's essay, it's crystal clear that these quantum spin systems are much more than just a curiosity of fundamental physics.
Absolutely. They represent a fundamental property of nature, this intrinsic angular momentum that we're learning to understand, control, and measure with increasing precision.
And that ability is unlocking pathways to potentially transformative technologies.
That's right. From revolutionizing computing with qubits to making electronics vastly more efficient with spintronics and enabling new kinds of materials and sensors, the impact is potentially enormous.
The significance for both science and society seems undeniable.
And as Yorgo Schneeppert concludes in his essay, the future looks incredibly dynamic. We'll see continued development of scalable quantum tech, exploration of novel materials showing exotic spin behaviors, and, as we discussed, that growing synergy with artificial intelligence.
It really is a field buzzing with potential. Schneeppert's essay offers a great roadmap to understanding it. Okay, a final thought for you, our listener. Imagine if we truly master these tiny quantum compass needles. If we can fully harness electron spin to process information and sense the world in entirely new ways. How might that fundamentally reshape technology, society, maybe even our understanding of reality itself? Something to ponder.